So, good morning. We continue with our simple function approximations of measurable functions to the main theorem. Last time we proved a lemma, or rather a theorem, under restricted circumstances for bounded measurable functions. Now we are going to prove the result in all general. So let us look at the statement of it. In extended real valued function real valued on a measurable set is measurable. If and if there exists a sequence phi n of simple functions on E which converge pointwise to f and has the property that mod phi n bounded by f or f on E f is non-negative you may choose phi n to be inclusive. So this is what we are proving, that if you have an extended real valued function f on a measurable set E is measurable when only if there exists a sequence of simple functions on E which converge pointwise on E to f and has the property that mod phi n is bounded by mod f on E for every n. If f is non-negative, then we may choose phi n to be. So we prove this theorem. One part of the proof. So we reverse direction. That means we prove the assumed existence of simple functions. Converging pointwise to and having all other properties that describe that. Then f being the pointwise, or what we claim is that so now f being the pointwise limit of a sequence of simple functions which is measurable on E. The limiting function now this we have already proved. So you refer to theorem. So this has been already. So this part is simple. The proof has been taken up in theorem. Right. Now what we prove is the forward direction of the implication. Assume f is an extended real valued function on a measurable set E which converges to which is measurable. Now what we claim is the following, that can be approximated by a sequence of simple functions and the other, satisfying the other state. Claim there exists a sequence phi n simple on E which converges to F, which converges to F pointwise which converges to F pointwise. Now what we do is we prove this assuming that F is non-negative, because that is enough. Okay, we prove this for it's enough to do that, because then for F we can write F to be equal to minus where both F plus are non-negative. So once you prove it for f plus, once you prove it for non-negative f, then it is automatically valid for f plus and f minus, and therefore you can use this formula to get the corresponding approximation for f, because what it would mean that there is some, say, phi n plus and some phi n minus. Okay, so that your approximation will be given by phi equal to minus. So that would give you the approximation, since phi n plus and phi n minus are both what you call simple functions. Their sum is also a simple function. Okay, therefore phi is a simple function, and this phi n is a simple function, and these phi n's would approximate f. So that's the strategy. Okay. So now we go to the proof. So we have assumed that f is positive. It's not negative. Let n be a natural number. Now we define En to be the set of all x belonging to E for which we have assumed f is non-negative, and we also now assume that, or mark the set En for which fx is less than or equal to. Okay, then clearly what you get is that n is measurable. Because En consists of all those x for which fx is less than or equal to 10. Therefore it is measurable. Okay, so clearly En is measurable. Now look at this function. So consider f restricted to E. Then we can apply the previous lemma to this function by the previous theorem. This theorem 9. To f restrict n their excess for epsilon equal to 1 by n. Simple functions phi n and psi n defined on n which have the following properties. What are the properties? First of all, 0, phi n, psi n. On secondly, see what you are doing is the following. See, we are taking up the function. Suppose this is your e. Then on that, suppose the function is something like this. This is the graph of the function. I am taking a rather smooth thing to give a feel for what is happening, and you can see that. Okay, right? So this is your f. Now what you do is, you know that's a non-negative function. You take En, define En as follows. So what you do is, you take f with the property that, or the restriction of f, En is such that fx is less than or equal. Therefore, what is this fn? Or what is this particular function f restrict that? See, this is your n. So you see, the En becomes essentially this is En. Okay, so we are taking this. Now what you do is, on En, forget about this portion now at all. This E slash En, you forget about it. En is a measurable set on which there is a new function defined, f restricted to En. Now for that, we can apply the previous theorem, because the previous theorem was primarily on functions which are bounded. Okay, so there exists. Now what you do is, so there what you had was, there is a given epsilon positive, there are functions, simple functions psi epsilon and phi epsilon, such that 0 less than phi epsilon less than or equal to f less than or equal to psi epsilon, and 0 less than or equal to psi epsilon minus phi epsilon, which is less than epsilon. Now, so here we choose epsilon to be equal to 1 by, and we use this notation phi n and psi n instead of phi epsilon and psi epsilon. Okay. Now, what is the approximation? Let us try to understand this approximation. Okay. So here we are not bothered about this portion at all. Okay. So what you are doing is you are dividing this. Okay, it's easy to. I'll not do too much of partitions, but maybe so much of partitions. So I'll get what I call, what you call, so this is the line. This is the line. Okay. Now what you do is the following. Okay. So you approximate on this portion. On this portion, approximate the function by this color coded from below by this. This is the approximation. This is your final. Okay. And on this portion, that is this part of the set. On this part, this is the approximation. On this part, this is the approximation. And on this portion, approximations. So you have a simple function, and similarly, this function is there, and then you have so you have this approximation, and then this portion approximates, this portion approximates, and further approximations on this one. So you see the function phi. So I'll color code it. Phi. Okay. Now let me draw the function psi n. Psi n is this part is this, and then you have on this portion it is this, and on this portion it's this. Okay. And over here it is going to be this one, and then this one over here, and then this one over here, and this is the approximation. So this is your psi n. Okay. So this is the step function that you have. This much, this much, this much, and this, and similarly, psi n is going to be this portion. It is this. On this portion, it is this. On this portion, it is this, and on this portion, it is this. This portion. Then on this portion, it is going to be this, and on this portion, that's an upper bound actually, but a constant function on this as far as this subset is concerned. And this one, of course, it need not be as simple as it appears to be here, because it depends on how complicated your f is. So this is the approximation. So you have phi n and psi n. Now if you look at, you see that at everywhere the function f is squeezed between phi n and psi n. Okay, so you see that if you take an x here, take phi n x, sorry, fx lies between psi n x and phi n x. Similarly, at all points, okay, this condition is satisfied. The other condition is that in between, so we have set the distance as 1 by n. I mean, I have not scaled it properly, but this is 1 by n. Therefore, the distance between phi n and psi n is going to be less than 1 by n. Now, this is the estimate that you have. This is the inequality that. So that gives an idea of how these approximations appear to. So you have this simple function approximations over here. Now what you have is the following. Now you observe that phi n is a upper bound for f on En. That is f restricted to. Now further, phi n less than or equal to psi n minus, this is less than 1 by n. So as n tends to infinity, you see that these two functions would come closer, and because of this property, see that f gets squeezed between psi n and, so that is done. Now that is done because we have got the existence of such phi n's and psi n's by virtue of the previous theorem that we. Now what to do? But function that you are dealing with in this theorem is not a bounded function. In fact, it is a extended real valued function with the possibility that at some places it is likely to take the value infinity also. Okay. So it's an extended real valued function that we are working on. Therefore, what we do is we have to extend this approximations over to the whole of E, from En to. Now let us do that. Okay, so let us do that. Now how do we do that? I extend phi n to E, because phi n is as such on En by setting phi n equal to n, phi n x So here what you do is, this is n. So what one does is, you just define this function, you extend this to the whole of n, this is your n. So on this portion you have to extend it. Here you set the function equal to that. Okay. So now what you have, this is a step function that you are talking. This is your phi. Okay. So we are not bothered about psi n. It's not important. See, there is a slight abuse of notation because phi n we had been using that on en, and this is an extension of that phi n over to the whole measurable set. And this property is satisfied on the entire. So we have got the approximation. Now what we do is we claim that phi n converges pointwise. Now this is, so we first use this case. Look at the points where f is finite. So consider points and choose an n, a natural number n, such that fx is less than n. That is possible because we are taking it as finite, right? Now what happens? Corresponding to this, you have then what you have is that 0 less than or equal to fx less than minus for every n greater than. Now that implies phi n as n. So phi n converges to f pointwise wherever f is finite. Okay. Now we take the case where f is not finite. That means f takes infinite value. x such that at that point what happens? Then what you have is phi n x is by definition this is equal for every n. Therefore, limit infinity, and which is the value of the function at okay. Now, so we have proved the result. Yeah, in general. Okay. Now, what do we need? We need some inequalities, or we have made a statement towards the end saying that, and therefore you see that phi n is less than or equal to, right? Now, what you do is, as I said, you take f and write it as f plus minus f minus, both are non-negative functions. Apply this result to each one of them, combine the things together, and then you eventually get. So, in the general case, it follows that this is that's easy. Now, what do we need? We need to make one more assertion that if f is non-negative, we may choose phi n to be increasing. This is possible because you replace phi n by maximum of now look at this sequence, the newly constructed sequence. Now clearly such a sequence increasing. Now the question that may come up is that all these are simple functions, so what about the maximum of this? That's also a simple function, and you see that these are all measurable, therefore the maximum of these functions is also a measurable function. All these things we have proved. Therefore what you get is you can essentially construct a sequence of non-negative functions which is increasing, and they are step functions, they converge to f points. Okay, so that completes the proof of this. Therefore, we have now set the stage completely for introducing the integral. And some more aspects about the convergence we will discuss in the next couple of lectures. After that, we go to define the integration. Now, the complete stage is set for defining the integral. As you can guess now, the integral of f is going to be defined by as the limit of the integral of phi n, and the integral of phi n can be easily computed because it's a simple function. Okay, for simple functions, integrals are easily computed. Right? Okay, thank you very much. With this, we conclude today's lecture.